Dhruba, you can start now.
I can start. Okay, thanks very much. Okay. Okay, good morning to all of you who are attending this presentation. So today and tomorrow, we will talk about active galaxies. But before we talk about active galaxies, I would like you to just think a little bit and probably perhaps enter in the chat box, those of you who are listening, about what do you think is a normal galaxy? What are the properties that would characterize a normal galaxy? So any suggestions in the chat box would be welcome. I will keep posing such questions as we go along so that you're also participating in the presentation and not merely just listening. Galaxies, I would like you to just think a little bit and probably perhaps enter in the chat box, those of you who are listening. Well, there would be a bunch of celestial objects. It could be anything. It could be an open cluster of stars. So that is not an answer to what is a normal galaxy. In equilibrium, not quite. There are a lot of things in equilibrium which is not a galaxy, so it doesn't really define that. So when you talk about a galaxy, what you mean is a galaxy is a collection of millions or billions of stars, depending upon how large they are. And as you've already learned, that they come in different shapes: spirals, ellipticals, irregulars, with bars, without bars, and even more complex shapes as we go early on to the evolution of the universe. But basically what we mean by normal galaxy is one whose properties can be understood in terms of its stellar population, a passively evolving population of stars, and the integrated properties of the galaxy is represented by this population. There is nothing exotic going on like jets streaming out from the nucleus and or varying quite rapidly. They usually are, as a whole, they hardly show any variability at all. So, for example, our galaxy, although it has a black hole, a supermassive black hole at its center, and Andromeda galaxy, our near big neighbor, they would be considered as normal galaxies, although there are supermassive black holes at the center and there is a low level of activity going on. But by and large, the properties of the galaxy can be understood in terms of its stellar population and the passive evolution of this stellar population. Now, then let's ask ourselves, what is an active galaxy? Okay, we don't say inactive galaxies, we just say normal galaxy and active galaxies. So when we talk about active galaxies, these can be broadly categorized into two. One is what are called starburst galaxies, and the other category is called active galactic nuclei. You have heard quite a bit during the course of this lectures of this refresher course in summer school about active galactic nuclei, but perhaps not as much about starburst galaxies. So I will just introduce you briefly to that. And what does it mean? What do we mean by a starburst galaxy? When we talk about a normal galaxy like our own, star formation is going on. You know that stars are formed in giant molecular clouds, which are the densest sort of component of our interstellar medium. They collapse when Jeans condition is satisfied, and they fragment and form stars. And when they form stars with a whole range of masses. But these galaxies, like our galaxy or Andromeda or what we call normal galaxies, have a reasonably small rate of star formation. Star formation rate is, for example, in our galaxy, is about a solar mass per year or so. Various estimates have been made using properties at different wave bands. And this is sort of a rough canonical number. It could be a few, it could be less than one, the estimates, but it's in the ballpark of a solar mass or so. But if you take a starburst galaxy, it could be not only 10 times more, it could be even 100 times more. Okay, and what you saw in the previous slide is an archetypal starburst galaxy, Messier 82, which is also a reasonably strong radio source and appears in the 3CR catalog of radio stars, of radio galaxies. Now, what you see over here in this part, this cursor which is showing you is the approximate orientation of the optical disk of the galaxy. And right in the central region, there is a starburst going on. And when you look at it at higher resolution or at higher energies, you see what is going on at the center. And you've already heard that to probe into the deep nuclear regions, you need long wavelength waves, radio waves, and these probe the central regions of galaxies, whether it be active galactic nuclei or starburst galaxies. And what you see over here are not only just diffuse emission, but you also see compact sources of emission. These compact sources of emission could be either supernova remnants, which are the remnants of massive stars which have exploded, or it could be regions of ionized hydrogen. And regions of ionized hydrogen, as you know, they are ionized by hot stars, gas which emit free thermal bremsstrahlung emission, whereas the supernova remnants, they emit non-thermal synchrotron radiation at radio frequencies and are polarized. So the structures of the objects also give you an inclination of the kind of objects they may be. When you see a shell-like structure, as you see in this image, it is more likely to be a supernova remnant, unlike H2 region. Okay, but you need more information to be absolutely certain. You can follow the evolution of these objects with time by imaging them with high resolution and understand the evolution of supernova remnants in different environments. But when there is a lot of star formation going on, there's a lot of hot gas which is generated and energy which has been input into the interstellar medium by these massive stars which have exploded. And they generate outflows from these galaxies. What you see in an axis which is perpendicular to this are the signs of outflow of almost all components of the interstellar medium driven by the energy output of the starburst, which is occurring in the circumnuclear or central region of the galaxy. At high energies, you also see exotic objects like hard X-ray binaries, which you talked about. And so you would see exotic X-ray objects as well from the center. But basically, it's an intense burst of star formation, which could be 10 to 100 or even more times larger than our galaxy. And M82 is a relatively quiescent, it's not the upper end in terms of starburst galaxies, but because it is close by, it's only about 12 million light years or so away, that we can study it in great detail and try and look at the properties of different components of its evolution, right? Now, starburst galaxies, this is another example. They're often found to be interacting with a companion, which perhaps triggers the starburst. And this is an image. The name is given over there, depending on its coordinates. And this is an object picked up from the Sloan Digital Sky Survey. And I've shown a spectrum of this galaxy on the right. And you can see that unlike in a normal galaxy, where the spectrum of the galaxy, as we shall see in more detail a little later, is governed by the integrated spectrum of the stars, and stars, as you have learned, are ones where they have absorption lines. So the overall spectra of normal galaxies will be dominated by the absorption spectra on stars, although they could be weak emission lines from nebular gas as well. But you can see in the starburst galaxy, because there is so much of hot gas which has been ionized by the burst of star formation, hot young stars which have formed, that you begin to see prominent emission lines. But these emission lines are narrow, they're not very broad, because the gas motions are relatively small, less than 100 or so kilometers per second. Now, let's look at M82, the first image of the galaxy which you looked at earlier. And what I plotted over here is the multi-frequency radio spectrum, a spectrum from radio to infrared wavelengths. At radio wavelengths, you can see, which is in the lower or the left-hand part of the figure, and on the right-hand side, you can see the infrared region of the spectrum. Now, let's see what the various components in a starburst galaxy might be. In a starburst galaxy, you have intense star formation, which is going on. And I might add over here and stress it again later, that this intense burst of star formation is not something which you can sustain over the lifetime of the galaxy. All the gas will be just exhausted. So these are brief episodes in the life cycle of a galaxy, but they have important implications in terms of their evolution, in terms of populating the intergalactic material with metals, if there is a strong outflow which escapes the galaxy. But these components, let's see what signatures we find in the integrated spectrum of the source. Now, at the radio region of the spectrum, which is on the left side, it is less than about 10 to the power of 11 hertz over there. There are two major components which are contributing to it. One, as we saw, are the supernova remnants. The supernova remnants have a non-thermal spectrum. That means it has a power law with a steepish slope. If S's flux density is proportional to frequency to the power of minus alpha, alpha could be about 0.5, 0.6, 0.7, etc. And so that is one component which contributes. The supernova event and the remnants also lead to generation of high energy particles which spiral in the magnetic field of the galaxy. They give out synchrotron emission. And as you have learned from Dipankar's lectures in the first week, that synchrotron radiation, unless it suffers from optical thickness effects due to absorption, also has a power law spectrum. So combination of both supernova remnants and diffuse synchrotron emission from the galaxy, the diffuse blob of emission which you saw a little while earlier, that gives rise, that gives rise to the non-thermal component of the radio part of the spectrum. Now let's look at the radio, what else could be contributing? The other component which I mentioned a little while earlier was the H2 regions, the regions of ionized hydrogen. And also referring back to Dipankar's lectures in the first week, they generate the thermal free-free Bremsstrahlung emission. Thermal free-free Bremsstrahlung emission, it is a thermal process. It is not polarized emission. And in the optically thin region, optically thin means where the radiation is allowed to come through without getting absorbed, then what you have is a spectral index of about 0.1 in the optically thin part of the spectrum, and it gets absorbed at lower frequencies where it becomes optically thick. So at the radio region of the spectrum, it's a combination of thermal free-free emission and non-thermal emission, which is generated by the ultra-relativistic particles moving in magnetic fields, whether it be in the synchrotron, whether it be the diffuse emission generated by the synchrotron process, or whether it be the supernova remnants which is generating it. Now you look at the right-hand part, that is the infrared part of the spectrum. What you see is that M82 itself is much more luminous at infrared wavelengths by nearly more than 2 orders of magnitude at its peak compared to the radio emission. Now, the infrared emission is due to dust, which is heated up. If it is too close to the star, it'll sublimate. But if it is sufficiently far, it's shielded, but it's still warmed up by the burst of star formation, then you will get infrared emission, radiation from the stars, which are reprocessed by the dust and is re-radiated in the infrared region of the spectrum. You can see that it looks like a black body spectrum. It's close to it. Emission gets modified with the properties of the dust. And you can see it's highly luminous in the infrared. But as I mentioned earlier, that M82 is not the high end of starburst galaxies. Its infrared luminosity is slightly over 10 to the power of 10 times the luminosity of the sun. Now, if you look at infrared surveys of the sky, which has been done since the infrared astronomy satellite, but more recently with more sophisticated high resolution satellites as well, Spitzer being one of them. And you will see that there are highly luminous infrared galaxies. If they're greater than about 10 to the power of 12 times the luminosity of the sun, they're referred to as ULIRGs. or ultraluminous infrared galaxies. Sorry, the second one should be 10 to the power of 13, which are referred to as hyperluminous infrared galaxies. This should be 10 to the power of 13. Okay, not 10 to the power of 12. So you can see that although M82 we can study in greater detail, it is still at the lower end of the luminosity of starburst galaxies. Now, what is the star formation rate? We mentioned a little while earlier that for normal galaxies like our own, it's within about a few solar masses per year. For starburst galaxies, it could exceed about 100 solar masses per year or so. And I said these are short-lived events in the lifetime of a galaxy because because the gas would be exhausted at when it is being consumed to make stars at this rate. And stars, as you know, are formed in the molecular clouds, which are the stellar nurseries where new stars are born. So I've just put some typical numbers over there. And this is another pair of galaxies which are actually interacting. This is referred to as antenna pair of galaxies because of the shape. You can look up images of this in Google. What I've shown here is just a central portion made by the Hubble Space Telescope, which shows the intense stars formation that is going on. And the blue color, these are real colors. So the blue color, as you know, are stars which are hot and young. They're young because their lifetimes are relatively short compared to the more sort of less massive galaxies like our sun, or even less massive than our sun, which live much longer because fuel is consumed at a much lower rate. But you can see this huge amount of star formation that is going on. So what are the consequences of star formation? So consequences of they are both in terms of star formation, they are both negative. They could be both negative and positive influence. For example, we talked about the huge outflows of gas from the region, from the galaxy, driven by these outbursts, these galaxies are known as superwind galaxies, and it drives out outflows of almost all components of the interstellar medium. It could disrupt molecular clouds and thereby reduce star formation. So it can have, depending on the physical conditions which are at place and location in the galaxy as well, that they could also be positive influences in terms of increased pressure in the in the interstellar medium, increased formation of molecular clouds, which could lead to increase in star formation rate. As you can see that these form stars at a rate about an order of magnitude or so higher than our galaxy. But these outflows actually play a significant role and the starbursts in terms of the evolution of the galaxy themselves and also evolution of the universe itself, because the metals which flow out, they populate the general intergalactic medium, affecting not only the properties of the IGM with time or with cosmic epoch, but also the galaxies themselves as they evolve with cosmic epoch. For example, many of the starburst galaxies are seen to be triggered by interactions with companions. NGC 4038 and 39 are two galaxies which are almost merging. But even without actually being merging or having merged, or a bigger galaxy swallowing up a smaller galaxy, some of it you may have listened to in Shomuka's lectures on both introductory lectures as well as the ones on clusters of galaxies. But even those would look relatively sort of isolated, could actually be interacting when you look at it at different wavebands and look for evidences of it. Now, I'm going to just show you three images of the galaxy M82. The one on the extreme left, this is M82 over here, and you can see that there are two companions, and these blue wisps which you see, they're wisps of neutral atomic hydrogen. The galaxies are what you see in this light white color over here. That's the SDS image. There's NGC 3077 as well. But what you see when you look at it in neutral atomic hydrogen, that means hydrogen which is cold, which is not ionized, and which you can detect, as you may have learned earlier, at a wavelength of 1420.405 megahertz, corresponding to roughly about 21 centimeters, due to the spin flip transition of the electron and proton spins being aligned and misaligned, and trace not only the extent of the gas, but also the dynamics of the gas. Here you can see that there is gas which is being stripped apart, forming tidal tails. And this is a neutral hydrogen image of this system. And right in the center where star formation is taking place, hydrogen is largely ionized. So you don't see much of hydrogen in the centers of these galaxies, but you can see that there is galaxy all around it interacting with the companions. And this on the rightmost side gives you just a velocity field of the galaxy. You can see not only that some of the gas is coming towards us, some of the gas is going away from you, redshifted or blue shifted. And so the thing is that even galaxies which may appear isolated at radio or infrared wave, at optical or infrared wavelengths, may have companions and be interacting with them, triggering star formation in the central region. Some of the momentum, angular momentum, is carried away by the tidal tails. Some of it, is which helps some of the material to go inwards toward the central region, triggering star formation, and also in cases with an AGN that feeding gas to the active galactic nucleus. Now, I just wanted to highlight a couple of things over here in this slide on star formation, which is that I've shown you examples of star formation or starburst galaxies in the nearby universe. M82 is a very close by one, about 12 million light years away. And so it has been studied in great detail. In terms of understanding our universe, what is important is to look at how star formation has evolved over cosmic epoch, how galaxies have evolved over cosmic epoch, how the gas content has evolved over cosmic epoch, because the gas content must be intimately related to star formation. And as you may have learned from Sherman's talk, that galaxies interact, harassing each other, tidally stripping each other apart, particularly in clusters of galaxies. And I showed you a pair of galaxies, the antenna pair, which are in the process of merging. And we also know from both simulations as well as looking at galaxies in various stages of mergers and evolution, that spirals can merge together to leave behind a profile which is elliptical. So combination or merger or spirals can give rise to ellipticals. That may not be the only way to generate ellipticals, but it is a viable process of generating ellipticals. So the stellar galaxy population, which you see, and its distribution in the nearby universe, as well as in the distant universe, are governed by all these processes. And we need to understand the detailed physical processes that are in play while trying to understand the cosmic evolution of the universe. Here is a plot which is often referred to as the Maddow plot from the astronomer who first plotted this, and it shows you the history of cosmic star formation from the nearby universe, which is at redshift 0, to the most distant universe, about redshift 8 or so, till where it has been estimated. And this is the look back time. This is close to about 13 point whatever gigayears. Go close to about 13 gigayears. You can see 12 gigayears over here. So very early stages in the evolution of the universe. Now, what you can see is that as you come from the very early stages, you'd have listened to some of the lectures by Kandu on structure formation as galaxies form, and galaxies form, that star formation keeps increasing till it reaches a redshift of about 1.5 or 2, and then it starts decreasing. Okay. Now, this is the cosmic star formation history in terms of solar masses per year per megaparsec cube, because you also want to know the star formation rate density. For an individual galaxy, we talk about the star formation rate, or you can talk about it in surface density as well. But when you're talking about cosmic history, you want to see what is happening per unit of volume. Now here, if you look at the picture on the right, you see that the star formation history has been, in this particular case, has been inferred from the ultraviolet emission and from the infrared emission. And I should mention over here that the infrared and the starburst, infrared and ultraviolet emission is due to the hot young stars. Ultraviolet emission, as you know from the blackbody spectrum, would have to be generated by massive stars, much more massive than that of our sun. Whereas the infrared radiation, as we mentioned earlier, is dust which has been heated to high temperatures by these massive stars which are forming, but not close enough that they get sublimated. And, and from a measurement of the ultraviolet flux and the infrared flux, and a knowledge of the mass function of galaxies, which one has studied in detail for different systems at nearby and moderate distances, that one tries to reconstruct this diagram. So in this sort of introduction to starburst galaxies, I wanted to give you a glimpse of this class of galaxies and also stress its importance in terms of trying to trace and understand the history of the universe. Okay? And these are very important components when we want to study cosmology and the cosmological history of the universe. There are also studies of the gas content of the universe, how it varies with cosmic epoch. But given that we have just 2 lectures to cover a wide range of topics, we'll let it pass for now. Now, again, having listened to this, I would draw you, for those of you who want to look at this subject in more detail, there is a nice review by Maddaw and Dickinson in 2014, relatively recently, and which is available in this, from the journal. You may have to pay to get it, but the same article is available here in archive, as well as the net link which I've given over here. Okay. Now, before we get on to talking about active galactic nuclei, I want you to sort of think for a moment that we talked about star formation rate estimates from the ultraviolet and from the infrared. While I talk about ultraviolet, I should mention that you are aware that short wavelength radiation gets scattered very easily. And that is why, whereas long wavelength radiation comes through, and that is why the sun appears red in the evening or reddish in the evening, and you have a blue sky. Now, similarly, if the ultraviolet light gets scattered, clearly there is corrections you have to make while estimating the star formation rates from ultraviolet, and people have worked a lot on it and have done that. But the question I'm posing to you right now for a couple of minutes, I'll let you think, or a minute or two, and an answer is that, can radio emission be also used to estimate star formation rate? And if so or not, what may be the pros and cons? So I'll wait for you to sort of reply in the chat window, and then depending on your answers, we will take it up. Don't feel ashamed of expressing your thoughts. It doesn't matter. I just want you all to think and participate. I will not call out your names and your questions. Let me give you a hint, since nobody has sort of responded in the first 10 seconds, is that just like infrared gets through without much scattering, radio waves can also pass through quite easily. And we saw that right in the central region of M82, we were able to map or image the central region of the galaxy, including individual supernova remnants and regions of ionized hydrogen. So, okay, Junik has said that, yeah, since it's a positive answer, I'm mentioning your name, I think radio emission can be used to estimate. The answer is correct. The answer is correct, but there is a caveat to it. What do you think may be the caveat to it? Radio from the center can come out, Gitanjali says, which is fantastic, which is also correct, that they are less affected by extinction or absorption. And so that is, from that point of view, is also a right answer, Gitanjali. But what may be the caveat, that why do you have to be careful? Why do you have to be a little careful? I'll just wait for about 10 or 15 seconds to see if any answers come out. All right. Somebody says only at particular redshift. We will discuss that. Okay. Rutwik says maybe it is easily mixed with other signals, so we'll have to be more careful. Suprabha says there might be other radio sources. I'm reading their names out because their answers are in the right direction. Rahul says radio emission can come from other objects as well. So these are going in the right direction. Okay. Now let me try and elaborate a little bit more. Okay. Gitanjali says other local radio sources, which is also correct. Rahul says radio emission from other objects, which is all going in the right direction. Because critical to estimating the star formation rate from the radio emission is that you're assuming that all the radio emission is due to the starburst. Okay, so if you have nearby galaxies where the active galactic nuclear component is not strong or very insignificant, there would be a correlation between, there is a very strong correlation between the infrared emission and the radio emission. And it is one of the very tight correlations in radio astronomy. But the problem with just blindly using radio is that there could be significant contribution from the active galactic nuclei, which may not be very easy to separate. It could be just the core of the nucleus generating radio emission, or it could be jets on different scales, which may not be resolved out in the existing observations. So that is the caveat which you have to bear in mind. On the right, I have shown a picture of line ratios. You can see this is just to tell you that these diagnostics have been used. We'll look at AGN a little bit more later, but these diagnostics have been used to see where do the starburst galaxies or the AGN lie. And there are overlaps. So for one object, it may not be, you cannot be, you have to hold your heart in your hands and say, hey, it's likely to be a starburst or a Seifert or some other AGN. But broadly, you can see that they lie in different regions of these line diagnostics. So if you're sure that your line diagnostics tell you that these are all likely to be starburst galaxies and the radio emission is generated due to the starburst, then you can do that. In fact, because radio can probe go to very low flux densities at the edges of the universe, it is sort of interesting to even stack signals or even combine sort of data from different galaxies and try and estimate rates of star formation from radio. So you're absolutely right that absorption is less, but one has to be careful about other sources of emission while trying to look at estimating star formation rates from the radio emission. So those of you who would like to get into or understand a bit more detail, then please do have a look at this review. It's a bit more extensive, but it's sort of quite nicely written. And it's relatively recent and is written by two of the leaders in the field. Okay. Now we'll come to the other part of active galaxies. And today I will spend just revising what you may have already studied earlier, but I will lay the groundwork for what we will do tomorrow. Okay. Now, characteristics of an active galactic nucleus, as you know, is high energy output from the nuclei of galaxies, often more luminous than that of an entire galaxy. It can outshine the galaxy itself, as in the case of quasars. The spectral energy distributions extend to the highest energies. You have collimated jets. You have very prominent emission lines, not prominent emission lines, which can extend up to thousands of kilometers per second. And you have often evidence of variability of the nuclear source or knots in jets on a wide range of scales and at different wavelengths. And we also see variability of the emission lines as well. So these are aspects which you are familiar with or which has been covered earlier. So my objective is just to draw your attention to these and also mention that each object may not show all the characteristics. Sometimes you might find an AGN with collimated jets, but relatively mildly variable at most. Okay, so they cover a wide range. And the kind of active galactic nuclei that you're familiar with, I've just given the X-ray luminosities over here. In each of my slides, you will find a reference at the bottom. Okay. 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 I just want to mention that I will share the PPT tomorrow after it's over and correct any mistakes which I find. So don't worry about taking notes, just listen and use your mind to think. Now, you can see that I've given normal galaxies over here, but you can see all these other active galactic nuclei, different categories, are much more luminous in the X-ray region of the spectrum. The host galaxies or Seyfert galaxies are usually spirals. These have been introduced earlier to you, so I will just rapidly go through them without spending too much of time. Radio galaxies are usually elliptical. There are a few cases where the hosts are spirals, but they are more the exception than the rule. And quasars, they come in both elliptical and spirals as their host galaxies. BLNAGs are by and large elliptical. And I've given examples of a few cases over here. So you can see that they're highly luminous objects. I've given high energies, but to distinguish them out. So these I will go through very rapidly, just to, it's more of a revision for y'all who have attended the previous lectures, that Seyfert galaxies, they're characterized by emission lines. It was noticed long time ago in 1908, first recognized optical spectrum of an active galaxy. Then Carl Seyfert was the one who did more systematic surveys of it and found that a significant fraction of spiral galaxies have prominent emission lines, unlike the normal galaxy like our own, which, as I mentioned earlier, are dominated by the absorption lines of stars. And hence, you know that stars are characterized by absorption lines. And when you add up all the stars together, you'll get an absorption line spectrum. So, but the Seyferts too are categorized into two types. And it is important for you to remember this because this is something which I will draw upon later. That there is one category of Seyferts, Seifert 1s, which are both narrow lines. Oxygen 3 you can see is narrow over here, but you can see H beta is quite wide over there. Okay, and I will mention about wide and narrow, as I mentioned over here. Narrow means widths up to a few hundred kilometers per second, whereas broad lines will be hundreds to thousands, often up to 10,000 kilometers per second. And they originate in a region close to the nucleus and it's referred to as a broad line region. Seyfert 2 galaxies have only narrow lines which are seen. Broad lines are either weak or they're absent. And they're intermediate types as well, but we don't need to bother about those in this lecture. So remember that Seyfert galaxies are hosted by spiral galaxies. They have a semistellar nucleus. They have prominent emission lines, and they are weak radio sources. And their optical spectrum can be broadly classified into those which have narrow as well as broad lines, and those which have primarily prominent narrow lines. The first one is called Seyfert 1, and the second type are called Seyfert 2. So, and they exist in all kinds of environments. For example, I've just shown you, when you look at the PPT, you can look at it in greater detail. They could be interacting, they could be in a small group, they could be fairly isolated. And that is true of both Seyfert 1s and Seyfert 2s. And I've just shown a collage of a few of them over here. Okay, and this is, I keep repeating about the spectrum of a normal galaxy. So I'm just showing you one over here to refresh your minds of a red galaxy in a cluster. And you can see that it is very different from the prominent emission lines you saw a little while earlier. They're dominated by the absorption line. This is at a relatively nearby redshift of 0.07 or so. This is a Seyfert 1 galaxy where you can see a broad H alpha line over here. You can see a broad H beta line. These are images I took from the Sloan Digital Sky Survey. And this is a Seyfert 2 galaxy. Again, you see that there are narrow lines. This is just to help you recollect. So Seyfert galaxies are one category of active galactic nuclei, which we listed earlier on. Radio galaxies also have been introduced to earlier. And you can see over here, this is a picture of Cygnus A, one of the very early radio galaxies to be identified and one of the very luminous ones. And the host galaxy is sometimes disturbed, but it is basically an elliptical galaxy. And you can see collimated jets of plasma squirting out from the active galaxy. And we shall see later that they squirt out at velocities very close to that of light, but as they travel further outwards, they may slow down. This is another example of a galaxy, relatively nearby galaxy, Hercules A. And I showed you these two pictures to just highlight another aspect of radio galaxies. That in the first picture which you saw of Cygnus A, the jet appeared largely one-sided, and they had prominent lobes of emission, on the opposite sides. But if you look at the galaxy which you just saw, that it hardly has any prominent hotspots at the opposite sides, and the jets are symmetric. So this is something which I would like you to remember as well, because this is something which we will come back to tomorrow. Here is another example. This is in the Virgo cluster of galaxies, M84. M84, the Virgo cluster of galaxies, and you can see that this is a lower resolution image of it. This is a blow up of the central region. This is the elliptical galaxy. This is the nucleus of the galaxy, and you can see pretty symmetric jets squirting out, and these have no prominent hotspots at the outer edges. So I will skip this for now, but you can look it up in the preprint a little bit more detail. This is just another example. So what I wanted to highlight over here in this picture is that the radio galaxies have extended lobes of emission, squirting out on opposite sides of the galaxy. But these ones which do not have bright hotspots at the outer edges often have more symmetric jets and are of lower luminosity generally, right? And this was a graduate student at Cambridge then, working with Julia Riley, Bernie Fanaroff. He's one of the leading lights of radio astronomy in South Africa today. And it is named after the two of them, Fanaroff Riley, class 1, and this is class 2. So class 2 objects have bright hotspots, asymmetric jets, although the outer lobes are reasonably symmetric. The low luminosity ones have symmetric jets and usually diffuse plumes of emission without bright hotspots at the outer edges. Okay, this is again the radio galaxies also. I'm giving you this information because we'll try and put all that together tomorrow. I will maybe just take 5 minutes extra to finish just a revision of the different kinds of active galactic nuclei. So radio galaxies also may sometimes have broad lines, but usually often they have narrow lines. So radio galaxies, on the basis of radio structure, they're classified into Fanaroff-Riley class 1 and class 2. On the basis of their optical spectra, just like in the Seyfert galaxies, they're referred to as the broadline radio galaxies and narrowline radio galaxies. While you're on this slide, I just want you to pay attention to this figure. Over here, you can see this is the spectrum of what is called a BL-like object, and you cannot see any emission. At the most, in some cases, you might see weak emission absorption lines, but it's essentially a continuum. So just remember that so that I don't come back to the slide again of a BL-like object. Now, quasars are the third category of active galactic nuclei that I would mention about. I will not get into too much of details, except that they were called quasars because initially, and today too, it appears star-like in Palomar Observatory Sky Survey prints or images which do not have adequate resolution. Adequate dynamic range to see the faint diffuse emission around them. Just as you don't see the stars when the sun is out, there may be a diffuse galaxy around a very bright nucleus, which you may not be able to pick up. 3C273 was one of the first quasars to be identified. There are very interesting historical accounts of how the object got discovered. So you might like to read it. And those of you who are interested, send me your email. I'll email it to you separately. But this object also showed a wisp of light, which we today know is a jet which has been emitted from the nucleus of the object. So quasars have broad emission lines. You can see over here the broad emission lines, H alpha, H beta, H gamma, etc. And it was the redshift of this Balmer spectrum, which was which was recognized by Martin Schmidt, which led to the discovery of quasars. They spent quite some time trying to figure out and make sense of the spectrum, because in those early days, in the 60s, early 60s, it was not expected that galaxies would lie so far away. And today we are probing almost at the edge of the universe. This is just a consolidated spectrum of what a quasar might look like. All right. Now, quasars, as I said, are abnormally luminous nuclei in galaxies, and it again took a long time to figure that out. Although there were hints from ground-based observations earlier, it was only when we were able to make very high dynamic range images with the Hubble Space Telescope. We also required very high angular resolution, because if the image became a bit large due to atmospheric seeing and was a bit fuzzy, all the galaxy around it would have been wiped out. So both high resolution and high dynamic range and very clever image processing was required to unveil the host galaxies which are around these abnormally luminous nuclei. And when we can do that, and we have confidence that we are able to see that, we can see that in almost every quasar to reasonable distances where we expect to see them. So quasars are nothing but galaxies with abnormally luminous nuclei generating huge amounts of energy. Okay, these are some of the other images which I picked up. QSO host galaxies, and QSOs could be radio loud, very luminous in the radio, about 10% of them, but the bulk of them are weak at radio wavelengths. The last category which I mentioned were what are called BL-Lacerté type objects. Okay, and that was the one where I asked you to keep an eye on the spectrum, and the spectrum was completely flat. Now, the discovery of this is interesting. I'll just mention a few sentences about it. That variable stars are usually named by a combination of letters AA, AB, AC, etc., and till a certain number. And then when they run out of that, leaving out certain combinations historically, they put V and a number and name of the constellation. So BL-Lacerté was classified as a variable star in the constellation Lacerté, but observations from a Canadian observatory, if I remember correctly, it's the Vermilion Radio Observatory which identified and pursued it. It was also cataloged in other observatories, that they found this optical object which looked star-like, and they thought, hey, another quasar, but no, because there were no prominent emission lines. So we took some time to figure out, where are these objects? Are they galactic objects? Are they extragalactic? So soon we converged on the aspect that they must be extragalactic. Firstly, they were uniformly distributed all over the sky. If it was in our galaxy, they would be more in the plane of the sky. And then some objects which had very weak emission or absorption lines definitely put it outside our galaxy. These are very strongly variable. Their optical spectrum is nearly flat, and they could be variable on timescales of days or less. And emission lines either weak or absent. So these are the different categories of active galactic nuclei, which we will try tomorrow to tie them together and see what we can learn from them. Okay? Now, I want you to just, before we close, and you ask me questions, I want to ask you two questions. One is, what is the source of energy in these luminous active galactic nuclei, where luminosities can range up to 10 to the power of 46 ergs per second? And secondly, what is the physical process responsible for the radio emission seen from the lobes of radio galaxies and quasars? I want to put here, I want you to, Gitanjali has promptly said accretion, which is fantastic, which is correct. But why do you think it's accretion? Can you justify why accretion is widely believed to be the process responsible for the emission? And also, what is the physical process? So I'll give you a few minutes to answer. I will interact with you via the Zoom group chat as you're asking questions. But after that, I'll leave it to the host to unmute and take questions. Supermassive black holes accretion, Arjun says, that is correct and beautiful. But why do you think that accretion must be the process and not something else? Gitanjali says energy calculation. I mean, it is correct. Nuclear process energy rate is low, so gravity can answer. That's why it's accretion. Potential matter accretion disk, supermassive black hole. Second one tells us can't be nuclear. Yes. Okay. Accretions is the most efficient process known apart from particle pair production. Ritwik says, okay. So excellent. That is fantastic. So is accretion because the energy which you require, particularly from a rotating curved black hole, the extraction of gravitational potential energy from the inner regions of the accretion disk turns out to be the most efficient process uh, in trying to understand the generation of this huge amount of energy. Also, the fact that you see jets in many of these active galactic nuclei, we today also understand how jets may form, although we don't have the final definitive answers, but we have very good leads on trying to understand how jets may have formed and the kind of accretion disk and magnetic fields that may play an important role in not only the generation, but the collimation of jets. Chetna says jets are magnetic field. Very good, excellent. And so you'll find that even nuclear energy generation processes, which occurs in the interiors of the sun and other stars, is not efficient enough to generate this huge amount of energy. In fact, when the large amount of energy was recognized, people argued that these objects can't be that far because and the redshifts are not cosmological. But today we know that redshifts are cosmological. We have strong evidences to support that. And we also have a good key on what the processes may be to generate this huge amount of energy. So Sumit says potential energy loss of particle during accretion. That's fantastic. Okay. Now we'll just take a few answers on the next question. What is the physical process responsible for the radio emission from the lobes of radio loud galaxies and quasars? What is the physical process? And I want you to give me a reason also why you believe what could be the emission process. We'll discuss that for a few minutes and then I'll take whatever questions the moderators might allow, and then we'll stop today. Okay. Sokia Shanbog says synchrotron emission, which is correct. Other than supermassive black holes, such quasars aren't possible. See, supermassive black holes, the accretion disk also generates thermal emission, as you would have learned from Ranjiv's talks on accretion disks. Okay. The jets carry magnetic fields and high energy electrons. Debadri says good. Those electrons firing magnetic field light out the jets and the cavities, they excavate, etc. Chetna says synchrotron emission, which is good. Okay. Okay. So I think what you all have said is correct. That that it is synchrotron emission by high energy particles. Saurabh also says synchrotron, which is good. Pooja also says something similar. So that's fine. So what is the physical process? It is synchrotron emission of highly relativistic particles gyrating in a magnetic field. And synchrotron radiation is something which Dipankar covered in the early stages of his lecture. Now, how do we know it's synchrotron? How do we know it's synchrotron? We know it is synchrotron because one of the characteristic signatures of synchrotron emission is that it is polarized. Okay, it is polarized, so we can detect polarization from the lobes and the jets of these quasars, and in the very diffuse lobes of these large radio galaxies, the degree of polarization can be high as about 70% or so. Whereas in the more compact objects, we see lower levels of polarization because of depolarization, which we will talk a little bit about tomorrow. So polarization of emission. The other thing also which gives a clue is the spectrum, because we have a power spectrum. Gitanjali says power spectrum, excellent. Okay, so both the synchrotron, the polarization of the emission, and the power law spectrum. Power law spectrum tells us that it is likely to be synchrotron emission. And this synchrotron emission, the power law can be modified at low frequencies by absorption effects and at high frequencies by radiative losses. If there is no fresh supply of high energy particles, then the high energy electrons radiate energy more rapidly, leading to a steepening of the spectrum at high frequencies. So thank you. Thanks very much to all of you for participating in the Zoom group chat and responding to these questions in the middle. But now what I will do is I will take questions which the moderators pick up and answer questions both from Pratik, who is Pratik Sagar and Santosh, who are the hosts of the Zoom, and Sumana, who's looking at the YouTube questions. So whatever you all tell me, I will try to answer. I'll try to answer. Thanks very much to all of you.
Hi. So I think the first question is by Sayadri Krishna. The mic isn't working, so I'll ask on their behalf. So the question is, do some galaxies show starburst as well as features of Aegean-like jets? Does that point to same relation between the two?
Okay, that's actually a very good question because yeah, lot of actually objects where we can study them in some detail, particularly in the nearby universe, actually they show evidence of an active galactic nucleus as well as starbursts going on. In fact, there are suggestions that M82 itself, from X-ray observation, have been suggestions it may host a nucleus. So the thing is that all galaxies with a bulge today we know host a supermassive black hole. So it's a question of what would help generate the huge amount of radio emission in terms of lobes, etc., jets which we see versus the starburst. So there are many systems where both occur, and in terms of the feedback which I mentioned earlier about starbursts affecting the interstellar medium of the galaxies, that is also true of the jets, for example, that they will actually provide a feedback to the properties to the host galaxy, to the interstellar medium of the host galaxy. And these are also an important contribution in terms of understanding the evolution of galaxies. So both in terms of cosmic evolution history of galaxies, we need to understand not only the star formation history, but also as also the evolution of the supermassive black holes in them, which Joydeep has been talking about, and also uh, um, the evolution of Asian activity in them. Because just because it has a supermassive black hole doesn't necessarily mean it will have massive jets. As you know, our galaxy, the Milky Way, also has a few solar mass, few million solar mass black hole sitting at the center. And our nearby galaxy Andromeda also has a supermassive black hole, somewhat more massive than that of our Milky Way. So just a galaxy, supermassive black hole existence alone does not guarantee that it will have a very active galactic nuclei. But to answer your question briefly, there are galaxies where both uh, coexist, and it's an interesting thing to see how they influence each other, and that is also an active area of research. Thank you.
So the next question is by Arjun, and could you please go back to the slide where you have shown the line ratios to differentiate between quasars and Seyferts? Hello? Did you get the question? Sorry, I didn't tell you the question, but did you get the slide? I think there is some issue.
Wait, it's coming.
I think he's back. Can you unmute him? Yeah, he's on mute. I think we need to unmute him.
Yeah,
Hi.
I'm okay.
Can you hear us? And
Yeah, I can hear you. I can hear you.
okay, so yeah, the question was pertaining about a slide of yours where you have
Which
shown
one?
the ratio of two emission lines to differentiate between quasars and Seyfarts.
Okay.
Question
One
is
sec.
about that, but I think you'll need to share the screen if possible.
Yeah, I'll do that. I will do that. One sec. Yeah. Can you see it now?
Yes. So the question is actually quite interesting. So the Arjun is asking, how does one come up with this kind of ideas? What is like scientific intuition behind coming up with this kind of scheme to differentiate objects like this based on ratios?
Okay. Okay. That's actually a very good question.
Yeah.
Okay. Now, what happens is that if you look at emission lines, all right, the question you have to ask yourself is when emission lines arise, they are being ionized, isn't it? They are being ionized by continuum photons. And in the case of stars, for example, you'll need photons from hot young stars to ionize the gas. Now, similarly, so depending on the energy of the photons, now you can go and see, for example, suppose you had an OB type of star, okay? And see, for example, the kind of temperatures it has from the black body spectrum, that what is the typical energy of the photons that you like to get out of it. Now, if you look at the AGN spectrum, for example, the AGN spectrum, tomorrow we'll have a look at, maybe I'll show a picture of the spectral energy distribution of an AGN, because the AGN spectrum extends to much higher energies. You can see, for example, although you have X-ray binaries, but you'll find that in the active galactic nucleus, the continuum extends more prominently to higher energies. So if you have high energy photons, then you would be able to ionize species or levels which require more energy to do that. So the intuition is to see what kind of photons are available, what are the line diagnostics that you can use satisfactorily. The other aspect which you have to bear in mind is also that, in these galaxies, because there's a lot of gas and dust, that the ratios, if they're very far apart, then there would also be dependence on reddening. The reddening will differ quite a bit from one wavelength to another. So you also try to take pairs of lines which are not too far away so that these corrections are small. But basically, it is the availability of continuum photons which will ionize species and also a given species at different levels, given the ionization potential of that particular line or that particular species. So that is what leads us to look at these lines. And in fact, what I've drawn over here is just O3 upon O2. This is just one example, but there are people, if you look at one of the references which I put over there is Cooley et al. So Lisa Cooley, she has been in the forefront of some of these activities, but people have tried out various combinations of lines. And one of the early attempts was done by Baldwin, Phillips, and Turlevich. And that is why these diagrams are also referred to as a BPT diagram named after them. But the diagrams have gone considerable refinement and revision since then. And they continue to be sort of looked at to see what is the best way, what are the best set of lines that can be taken. But these are the basic governing principles which lead us to sort of look at these aspects.
All right. I think there are no more questions here, but there are 3 questions on YouTube. Do we have time for that? I think we can take some.
If Sagar and Santosh allow, I'm happy to do it. Yeah.
You can have one or two.
Yeah, we can do so. Okay. So Ankit Ganguly on YouTube has asked, has the Milky Way passed the starburst phase or is it yet to enter it?
Milky Way has not actually, Milky Way, what is happening is that we know that the Andromeda Nebula is moving towards us. Okay. So Andromeda and the Andromeda Nebula and the Milky Way are going to collide. And I would suggest that you look at some of the simulations which are already there in the web of how this collision might proceed. But don't panic or worry, because it will be a few billion years from now, and we'll probably destroy ourselves by other means before Andromeda hits us. So there is likely to be a burst of star formation when Andromeda and our nebulae and our Milky Way sort of collide. But right now it is passively making stars at about 1 solar mass per year.
So are you going to take the this mechanism for formation of jets tomorrow? Are you going to touch upon that?
I will not touch upon tomorrow actually what I was planning to do, because it's difficult to cover too many aspects. I was planning to cover about a little bit about jets, but basically to understand about the asymmetry of jets and a little bit about the unified scheme, because those two have not really been touched upon.
Okay,
I think planning to talk about launching of jets, so I will leave it to him.
Yeah. Okay. Yeah, there's just one last question. Is it possible in starburst galaxies with supermassive black hole that there are other small black holes around it which are continuously falling inside it and making it bigger and bigger?
See, continuously falling, we don't know. But for example, if you take our own galaxy, okay, take our own galaxy, that there are supermassive, they're not supermassive black holes, but they're black holes of different sizes across the galaxy, because there are these X-ray binaries, which are binary systems where one component is an X-ray. Then besides the supermassive black holes, which are in the ballpark of millions of solar masses, we also know of existence of massive black holes from the detection of gravitational waves. So black holes occur in a range of masses, and the supermassive black hole is what resides in the center of the nucleus, center of the galaxy, and is related to the properties of the bulge. But if there happens to be a galaxy, a black hole near the supermassive black hole, it could be swallowed up, because we know and have evidence of stars near the supermassive black hole being tidally stripped by the supermassive black hole. So there's nothing to stop it from supermassive black hole swallowing up a smaller black hole in its vicinity. But even excluding that, there are black holes of different sizes, masses, different masses occurring throughout the galaxy. But the most massive ones, the ones in millions of solar masses, which are called supermassive, they are only in the centers of the galaxies. Yeah.
Yep. Good. I don't think we have any further questions. So yeah.
Okay. Thanks very much to all of you.